In the year 2000, the chief scientist at Yahoo at the time went to Carnegie Mellon to give a talk about the 10 biggest issues Yahoo was facing at the time. And one of these issues was a spamming issue. At the time, we were being flooded with spam mail between, I don't know, tickets to some unknown event and medications we never heard of. And the issue was real. In the crowd, there was a young PhD student who heard about this and was like, hey, that's an interesting challenge that Yahoo has to face. I mean, the best that they could do was mitigate the amount of mails an account could send a day to about 500, but he knew that the spammers kept on spamming. So he took it upon himself for the following days and weeks to think of a better solution, something new. And after talking with some friends and some colleagues, he came around the understanding that this was really an issue of determining between computers and humans. Because humans could only send a handful of emails a day, but computers, they could send them at scale. And this young professor, he knew one other thing. He knew that Google at the time was trying to upload all the books in the world to the internet. But the challenge that they had doing it was that computers couldn't read text. So they had to decipher these pictures of books into digital books, which was very costly in time. So this young PhD student, he knew he could build an algorithm where you could take a little piece of text, put it in front of the user trying to sign in, and a human would pass this easily, but a computer would have a lot of trouble. He sent off this algorithm to Yahoo. Within the week, they implemented it, and with a few tweaks, he sold it off to Google for a couple $1 million. And at this point, you guys are probably asking yourselves, I'm at an ETH Denver event, at a Bitcoin blockchain summit. Why is this guy talking to me about reCAPTCHA? And that would be a good question. Hi, my name is Eitan. I'm a software engineer, second-year software engineer at Starkware. And what I haven't told you yet about this story is that this solution actually succeeded another solution that was spoken about in a paper 8 years prior in 1992, co-authored by a man named Modular L2. In this paper, it spoke about this concept of proof of effort. How if you could push computers to run a certain computation for about 10 seconds, then you could reduce the amount of mail being sent around the internet. And although this solution was succeeded by reCAPTCHA, it eventually found a home about a decade and a half later with Bitcoin and blockchain, in a new term known as proof of work. And this story, it's kind of similar to zero-knowledge proofs, where in 1980s, when they were first being researched, nobody had any real idea what the use case would be of it. But only in 2013, when a man named Eli Ben-Sasson came around and realized that this challenge of scaling blockchains could be solved by zero-knowledge proofs in a new form known to be as Starks. And what are Starks? So let's give a bit of a background. So let's put in a black box for a second, the tech behind the Stark. And let's focus on what it does. So scalable, transparent arguments of knowledge. Basically what they allow us to do is take strong sequencers and execute transactions that can later be proven by a wide range of weaker, cheaper full nodes, thereby decentralizing a network at scale. And today at StarkNet, we implement this solution when settling to layer 1. And it does take a bit of time to do so. But eventually, we'll be also doing it at the layer 2 level, which will be in a body to be known as proof chains, which we'll get to later. Because the question with this is, why are Starks important to you guys as app developers? So let's start off with, here we go. Let's start off with a question of how can you run a DApp on a centralized layer 2. And that question, it's not too straightforward because it brings another question to forward, which is what is the state of your DApp at any current point in time? I mean, you could rely on the layer 1 state of the network, whatever gets finalized to layer 1, and say this is the state of my DApp. Or you could rely on the centralized layer 2 state of the network. But there's trade-offs going both ways. If you're waiting for layer 1, it could take a bit of time. But if you're relying on layer 2, you're relying on a centralized source. And let's say you were to rely on that centralized source, and with that, run your own node in the background, re-executing all the transactions that still haven't been settled to layer 1. Well, that could also be timely and costly. And let's say that node was to fall, you'd have to bring it up again and re-execute again, which again is costly and timely. So it brings to question, all right, that's on a centralized layer 2. How does it look on a decentralized layer 2? Why run dApps on a decentralized layer 2? And the first win we get from that is that it's trustless because it's decentralized. But the second win that we're looking for is to be able to improve the amount of time it takes to trust that a transaction is valid on the network. Remember beforehand, we had to, if we were relying on a decentralized state, we'd have to wait till it was settled to layer 1. But if we can do that on layer 2, then we can actually get a verified state of the network, of the decentralized network, a lot faster. And that's what we're going to talk about right now. So how can we do that? What's the goal of achieving that? To quickly verify a decentralized state. The proofs of these states, remember we spoke about Starks before. So Starks are proofs and validating those proofs. So those proofs of those states, we want to be able to see them pretty quickly after the creation of the block. And a naive approach to that would be, all right, we built a block. How about we build that proof right away and put it in that block? And the issue with that is that proving takes a bit more time than building the block. So it brings this idea of a different solution where each block contains a proof of the block that appears k blocks beforehand. Meaning, let's say we're at block 20, k is equal to 10. So we put in block 20 the proof of block 10. And how is 10 decided? Well, it's the amount of blocks that are built in the time it takes to build a proof. So how would something like this look? Well, a Stark proof for block H would have to include 2 statements. The first one being the transactions of block H are valid, and they produce the given state of the network. And the second statement would be that the proof of block H minus k is valid. And what this solution could give us is something known as proof chains, where we have a couple different chains of proofs, and those chains cover all the blocks of the network. So let's look at the first example. When building block 9, let's say k is equal to 3, it would include the proof of block 6. And in block 6, you would have the proof of block 3, and so on and so forth. And the same thing with block 10 and block 11. And essentially, by doing so, you would only need to validate the proofs in blocks 9, 10, and 11 to be able to prove the whole state of the network. Now remember how much time it takes to re-execute all the transactions between layer 1 and layer 2. Let's say you were running on a centralized network, and you were running a node in the background to re-execute all those transactions. Well, in this solution, you can do it by just validating k blocks instead of re-executing all those transactions. So let's talk about harnessing this rock-solid foundation. Well, it speeds up the state of verification because now, as I said before, you don't need to re-execute all the transactions between layer 1 and layer 2. And it also reduces the vulnerabilities that a DApp would have when building on such a solution because you no longer have to trust the layer 2. It's decentralized. And that leaves me with a question of, well, remember that spamming issue? Now that you have this rock-solid foundation, maybe it's your turn to find that new technology that has a use case here. And hey, maybe you'll sell it also for millions. Thank you. I also don't have any QR codes. They weren't working. But you can find me afterwards if you want to exchange information.
Thank you, Eitan.